Okay, working on multiple choice set 1 for work and energy, and we're going to look at numbers 3 and 5 for this one. Alright, I like 3. 3 is one of those situations. It's an extremely simple situation in its description, but understanding the physics of it, it's one of those things that I would encourage you to, when you really start thinking in terms of physics, taking things that you just take for granted every day and seeing how the physics applies is a great way to go about doing things. So a person holds a book at rest a few feet above a table. The person then lowers the book at a slow, constant speed and places it on the table. Which of the following accurately describes the change in the total mechanical energy of the Earth book system? So we have, here's our table. We'll say the book starts somewhere like up in here. Now, at this point, it certainly has mechanical energy. Because it has gravitational potential energy. Remember, mechanical energy is the sum of an object's kinetic energy, gravitational potential energy, and spring potential energy. But of course, no kinetic because it's not moving initially, and the spring energy is no spring involved at all. So really what it has is gravitational potential energy. Alright, so fine, no big deal. The person doesn't drop the book. Because if they just dropped the book just before it got to the table, when it's at the level of the table, it would be moving. And it would have turned that potential energy into kinetic. But the person lowers the book down at a very slow, constant speed. So there is a little bit, here's where I admit some things that could be confusing. There is a little bit of time here when gravity does speed up the book from rest. But then it's exchanged, the hand slows it down here. So we're not going to worry about that. What we're looking at is the book starts here, and then the next time we're told to look at it, the book is on the table and is at rest. And so, is there a change in its kinetic energy then? I'm sorry, in its mechanical energy? Well, seems to me that there is, because here it had something, it had a gravitational potential that wasn't zero, right? Some number, mgh. But here, presumably we would have set this level at 0. Here, its mechanical energy is definitely 0. It's not moving. It has no more gravitational potential, assuming that this is h equals 0, or y equals 0, depending on how you want to look at it. And of course, spring isn't involved at all. So there is definitely a decrease. So where did the energy go? Well, all right, the quick answer is it must have gone to thermal. But where? Well, as the book was lowered, the person's hand, so here's the book, I'll slide over, here's a picture of the book as it's being lowered. The person's hand is applying a force, a normal force by the hand, upward. That is, if it's moving at constant velocity, the same as gravity, the weight. And so, while the book moves, downward. So this is doing negative work, and at the same time, this is doing positive work, but they're the same force and they're moving the same displacement, so the net work done is 0. So the kinetic energy doesn't change, but the potential energy does decrease. Now, the thermal energy involved that we said it has to go to is in the person's muscles. As they lower, their muscles exert heat, and that's where that energy goes to. So it's the heat generated as you lower. So the mechanical energy is removed by the external force, the non-conservative force of your hand pushing up on it. This is what causes the energy to quote, disappear, to go to a non-mechanical form. So the mechanical energy here is 0. So I haven't even looked at the answer possibilities. Let's see if any of them make sense with what I just said. Total mechanical energy is unchanged, not based on what I'm looking at, because there's no change in the book's kinetic energy. Well, true. The total mechanical energy is unchanged because no work is done on the Earth book system when it is lowered. That's not true. There's no net work done, but there is positive work and negative work being done. The total mechanical energy decreases because the person does positive work, close, on the book by exerting a force that opposes the gravitational force, Close. I don't like this part though. Total mechanical energy decreases because the person does negative work on the book by exerting a force on the book in the direction opposite to its displacement. I'm liking D. That fits with what I just described. I'll check it to make sure, just so that, you know, nobody thinks of me as a liar in this case. Let's see. Let me see that. Oh, okay. And we're looking at number 3, we said. And my sources tell me that I am, in fact, correct. Yay. All right, looking at number, what's the other one? 5, I believe. All right, so 5 already has some writing here. We're going to, I don't want to give it away, so let's look at 5. The idea is this, is you have a car that it's initially going at some velocity v. Let me put this up a little bit. There we go. So it moves some velocity v, and the car's got some mass m. So it therefore has a kinetic energy of 1/2 mv squared. M and v being the mass and the velocity here, no big deal. It slams on its brakes. Friction is the force that opposes the motion, so friction points this way and slows the car down until it stops, where its kinetic energy is obviously 0, giving us a change, and we'll squeeze this a little more, there we go, giving us a change in kinetic energy of, we'll put the negative in, negative 1/2 mv squared. So if you come to a stop, your change in energy is really just the same as the initial energy. A negative sign because you lost it. To do that, your brakes apply a frictional force over a certain distance. All right, so this change in your kinetic energy is equal to the work done by friction, because that's the only force acting on it at that, the net force acting on it. Of course, normal and weight would be there. So the net work is equal to the change in kinetic energy, and for this scenario we have force of friction times whatever the displacement is equals, we'll just go with the magnitude, 1/2 mv squared. If you, the force would be negative, and so would the change in kinetic energy, so the negatives would cancel. Really just worry about magnitudes here. Okay, so this is true for a car that slams on its brakes and comes to a stop. Now we're going to look at the same car, but with a different starting velocity. And one of the things I want you to, the only thing, well, the big thing that carries over from here to there is this. I mean, obviously the mass of the car stays the same, but when you slam on your brakes, you have the maximum force you're going to get, and you're not going to get any more. There's nothing you can, there's nothing you can do about it. So whenever you slam on your brakes, whatever that maximum force is what it is. So that will not change. All right, so then we go to a new situation. In the new situation, the car is going. Now the problem there is just twice the velocity. I'm gonna do a slightly different scenario in the hopes that you'll take this and be able to apply it to that problem. The scenario I'm doing is actually more complicated, but not by that much at all. So let's pick a number. Let's say the velocity is 6 times more. So now it's going 6 times as fast, still has the same mass. It's booking. Slams on its brakes and comes to a stop. Now, my drawing will not be to scale, trust me, but I think we all would agree it's going to take longer to stop. Here, its final velocity is 0 still, and so what's its kinetic energy initially? Well, it's going to be 1/2 the mass. The velocity is what we're calling 6v, 6 times the other one, but remember, we square that. So your kinetic energy at the beginning is 1/2 m times 36v squared. Now, we don't have to write that. You could like take half of the 36, but I wouldn't do that in this case. Because if you recall, the initial loss in kinetic energy from the earlier case, the one that was on paper earlier, was a loss of 1/2 mv squared. I want to keep that. I want to keep that form down here. So in fact, my change in kinetic energy, I'm going to look at it as the following. I'm going to take this 36 and just write it out front. 36, that's not even remotely a 6, that's a K. There we go. Times 1/2 mv squared. So I just move that 36 out to the front. So in this case, there's my change in kinetic energy. It would in fact be negative. That would be equal to the work done. All right, so the net work done is equal to change in kinetic energy. I have net work as being the force by friction, which remember is the same as it was before. The car cannot produce any larger force, times the new stopping distance equals the new change in kinetic energy. So that's 36 times 1/2 mv squared. Now let's go back to what we had earlier. So I don't think I quite finished this one out a second ago. That means that the stopping distance here is 1/2 mv squared over whatever the braking force is. All right, so I didn't quite finish that one out. So there's the stopping distance right there. And just divided both sides by the force. If I go to the new problem and I solve for this stopping distance, the new stopping distance is 36 times 1/2 mv squared divided by that braking force. But all of this right here is just the old stopping distance, the original one, when I was only going at V. So now I'm going my new distance, stopping distance. Is really 36 times my old stopping distance. So that factor of 36 shows up. So the quick version is if you make the speed 6 times more, the kinetic energy goes up by a factor of 36, which means the stopping distance is also going to go up by a factor of 36 because you can't change the force. So if you apply the same idea, so we can just run through a bunch of scenarios. If I have a velocity of v and later I triple the velocity to 3v, then what's my change in kinetic energy? It's going to be if the kinetic energy here is, whatever, Ke, this is going to be 9 times that Ke. All right? If I have the velocity is v and I make it 5 times more, if this is my Ke here, then I'm going to have 25 that amount of kinetic energy here. So use that same principle, and therefore, by the way, 9 times the stopping distance and 25 times the stopping distance. Okay, so apply that principle and see if you can get a decent answer for that one, which I believe is number 5.